All right, so today I'm still doing some more calculus. This time I'm not doing any more revolutions of surfaces where I'm spinning. I'm going to be doing cross sections. So we're going to be finding volumes of solids with known cross sections. Volumes of solids with known. The key to getting this section or understanding how to do cross sections properly is knowing how to connect the two graphs together. Because whatever you connect together, you're going to use that to find your area. So if you know your area formulas from geometry, even if you don't know them, normally those formulas will be given to you. If you know how to find those two graphs and connect them, you can find any area, and from any area you can get your cross sections. So here's the main thing right here. To find volumes with known cross sections, volume is equal to the integral from a to b of a of x dx. And a of x basically just means area. And the reason why we don't write anything in particular there is because the area formula is different based on whatever shape you're dealing with. So depending on your shape, then that's the area formula that you'll put here. So that changes based on the shape. So this is the first thing I'm going to start with, this right here. I have two functions here. That's what we're going to start with first. So I'm going to set these two equal to each other first because I need to at least know where these graphs will end up, intersecting. All right, so what I'm about to do is I'm going to take my f of x and my g of x. I set them equal to each other, and then I'm going to start collecting everything over in this direction. So x squared is going to stay on the left side of the equal sign. That's going to come over here as a positive x. That's going to come over here as a negative 2. Now that's equal to 0. So I've gotten those two over here, right? I made sure that the signs did switch, and now I can start factoring on this side. So what I'm doing right now, this right now isn't even calculus at the moment. Right now we're doing some algebra, just solving for some unknown variables through the process of factoring, which is extremely important. And so there's my factors right there. And that gives me two solutions. Either I can put a positive 1 here, that'll give me a 0, or I can put a negative 2 here and that'll give me a 0. And that's how I get my two intersections. So I know I have an intersection that happens at positive 1 and negative 2. And this is what my two graphs will look like if I were to put them on graphing paper. It'll be a parabola here, and then it'll be my line that drops through in that direction. We just found out that they intersect here and here at negative 2 and positive 1. So when I start the process of finding my cross sections, I need to know how these two connect to each other. In other words, I need to know which one is at the top, which one is at the bottom. So if you follow this dot, g of x is at the top, and f of x is the parabola which happens to be at the bottom. All right, so I have a top minus bottom. That top minus bottom comes up in a lot of different sections, whether we're doing area between curves, if we're revolving surfaces, and when we're doing cross sections. So understanding how to do a top minus bottom if we're vertical, or right minus left when we're horizontal, is going to be extremely crucial. All right, so I'll just rearrange this so that I don't start off with a negative. I'm going to head and put my 2 in the front. Put my negative x in the middle, and then my negative x squared on the end. So my side is equal to this. That's how long this side is. At any point in time between negative 2 and positive 1, this is the length. I'm about to start with my rectangle with a height of 3. We have everything we need to figure out the volume with a known cross section now. So we have a rectangle, and I can't even spell. Okay, there we go. So we have a rectangle with a height of 3. Okay, so before we get to the volume part right here, because I know I'm going from negative 2 to 1, the question is what goes here? I like to scratch my stuff out first before I put it in here to make sure what I'm looking at is correct. And remember, to find the area of any rectangle, to find this area, you need to know what this is times that. Get what I'm saying? So if I know this length and I know that length, all I do is multiply the two together and I have the area. Now, remember, because the part of this rectangle sits right here, S is going to be the part that it's standing on. Your rectangle is going to stand on your S, so that's how long it's going to be across the bottom. And then right here, I came up with a height of 3. I said, okay, let's see what this will look like if we had a height of 3. So that means my area is going to have to be 3 times all of this. Remember, this times this is your area. That's what goes here. All right, so I have a rectangle at a height of 3. So I do 3 times that side with respect to the x-axis, and I'm going to integrate from -2 to +1. So as I slide that rectangle all the way across, it's going to calculate all the areas and give me that answer. Now, I'm not going to work out this part and get the answer yet. I just want to set them up first. So this is what it will look like if you set up for a rectangle with a height of 3. If the height was 4, then that'll be a 4. If the height was 5, then that'll be a 5. All right, now, what if I wanted to figure out the cross sections if we were looking at cross sections that are the shape of a square? So we got to think about the area of a square, and from there we can set up. And the cool thing about finding the area of a square is if you know one side, then automatically the other side matches. That's why we say the area of a square is s to the second power. Second power, we call that s squared because that's what squares do. All right, so I already know my s. All I had to do is throw parentheses around it and put a second power on it. And then I've set up my next integral. So in other words, I know my volume will be equal to my integral as long as I'm going from -2 to +1. My s happens to be 2 minus x squared. But that's just a side. This side has to be squared. And this one right here would give me the volume if my cross section was a square, because I took the side and raised it to the second power. Now the semicircle one, that's the one that's the trickiest. And I'm going to explain why in 1 second. But the semicircle one is the trickiest one. Out of all the shapes that we deal with, the semicircle is the one that gives students the most problems. All right, so the reason why is when we find the area of a circle is pi r squared, right? But when we find the area of half of a circle, it is pi r squared, but it's divided by 2. So that part right there is the part that trips people up. The second thing is S happens to be the full length, not half of the length of this circle, all right? So S will be equivalent to your diameter right now. What we need is half of S, then we can put that in there, all right? So instead of putting S is equal to 2 minus x squared, I have to do 2 minus x squared divided by 2, then put it into the problem. So that's the part that makes it tricky. So my length is 2 minus x squared, and I have to split that in half so that I can get to the radius. So that can act as my radius. So when I divide it by 2, what I'm getting is this much of it. Now I could come over here and do my pi r squared divided by 2. See that? Pi r squared divided by 2. And remember, the volume will be equal to the integral from -2 to +1 of pi r squared divided by 2. And once again, this will calculate out and give you the volume. So these are the 4 most popular shapes that we go through when we do volumes with known cross sections: rectangle, square, semicircle, equilateral, triangle. The equilateral triangle, this is the area for an equilateral triangle. It's extremely simple to the area, similar to the area of a square, because the area of a square is s squared. The only thing you have to remember is 3, 4. If you can remember square root 3 over 4, all you do is stick that right there on it, and then boom, you have your area of an equilateral triangle. So if I want to set up my volume using an equilateral triangle, literally I'm going to write down my side squared, which is 2 minus x squared to the second power, just like you would for a square, and then just put a square root 3 over 4 in front of it. And what I have here are 4 different volumes based on different shapes to find the volume with a known cross section. So the next few minutes now, we're going to actually take a look at what these shapes look like using a computer program. All right, so this is the first one, the one that had to deal with the rectangle, part A. When I punched it into my calculator, it gave me the area of 27/2. And if you know how to calculate that out, that's basically 13.5. So the volume would be a 13.5 with a known cross section of a rectangle with a height of 3. All right, so I verify one more time. See, I put a dot on the rectangle, height of 2. I'm starting at -2. I'm stopping at +1. So I'm starting here and I'm stopping there. So it's going to cover this area here. And even when I say volume, look what it says, 13.5. Now it has a negative there, and that's just because of the way I have these numbers arranged at the top. Bottom line is the absolute value, you just get rid of the sign. So we're looking at a 13.5 area. Now, let me see. It says we're going to take a look at the solid next. All right, so here's how it looks like if I were to view this from the top, right? If I'm looking straight, if I was flying in the sky looking directly down, this is what this would look like. Now, remember, we're talking about a solid in 3D with a cross section that's a rectangle. So the shape that it would make would be something like this. See that? That's what it looks like in 3D with a height of 3. All right. Now, the cross section part is the hardest part to visualize. So if I start peeling these layers back, and then you looked at it from the front end, right? Let me turn it this way. That right there is a rectangle. See, there's your side, that's your height of 3. This is your S, and this is your height of 3. And there's your rectangle. So every time I peel back a rectangle, I know the area of that rectangle. I know the area of this one, that one, that one, that one, that one. And I know the area of every last one of these rectangles. I know the area of this rectangle, and every time I do this, I'm calculating until I get to the end, and now I have a volume. That's what this looks like with a cross section that's a rectangle. Okay, now I'm going to switch this over to a square. We're going to look at the volume. Look, the volume is 8.1. So the volume changes based on the shape that you're dealing with. So let's see what this shape looks like as a square. And I know it's kind of confusing. It's really weird looking. Why does it look like that? So we're going to take a look at this from the top. This is what this looks like from the top. I think I had a C here. And so like if I were to peel this back, see that? So let's see, from the top, this is what the graph looks like when you draw it on paper, just drawing your line and your parabola. Now what I have to do is do one of these numbers, so as you peel it back, you can see where the squares come from. And there it is. I don't know if you noticed that, but that's a square. This length is the same length as that one. So every time I peel it back, it's going to be a square every single time. And so the reason why this one makes a shape that's slightly different from that one, the rectangle, we were locked at a height of 3, so it stayed the same height the whole time. It's almost like a loaf of bread, you know, it looks exactly, the top and the bottom look exactly the same, and they are parallel to each other. But because we're dealing with a square, if the base is short, the height is short. If the base is tall, the height is tall. So depending on where you at in the graph, the square can get really small or it can get really large. So that's why cross sections of a square look like it's like an acorn shape or some type of walnut. I can't remember the type of nut I'm thinking about that has those sharp edges kind of like this, but that's what it reminds me of. So that's what it looks like from the top, 2 dimensions. Start rotating and looking around it. This is what it looked like in 3 dimensions. And this one is a square. Cross sections is a square on this one. All right, now we're looking at a semicircle. Let's see. The volume of the semicircle is 3.1806, so on and so forth. So if I wanted to look at the solid, this is what that solid looks like. Really weird looking shapes. And what we're doing is we're finding the volumes of all these weird shapes, like literally on paper. It's kind of funny how that works, but it works. Once again, from the top, there's my parabola, there's my straight line. Then I lay it flat. Then I start looking at it from the front side. And as I peel the layers back, you'll see why we call this one a semicircle. And you'll start to see the semicircles. And there they go. And there's your semicircle right there. That's a semicircle, half of a circle. So that's what it looks like when it being half of a circle cross section, if you were to slice it. Peel it all the way back. Goodness gracious, come on. So yeah, we peel that all the way back. All these semicircles. It's like a whole bunch of semicircles. And all the way to the end. Boom. And that's what it looks like using cross sections of a semicircle. This is what it looks like. So I'm gonna go ahead and rotate all the way around it so you can see it. Top, bottom, front, back, semicircles. All right, now this one is my equilateral triangle. Equilateral triangle, look at the volume here. 3.504740. That's my volume. Take a look at the solid. Let me see from the top. Oh, it's kind of weird. Okay, there we go. All right, so this is what it looks like from the top. And that right there, that line that you're following, right there down the middle, that's where the points meet. The tip of the triangle, when you have a triangle, the little top part, that's what we're looking at right here. So it creates that line there, but this is what it looks like directly from the top. Now, if I go back to the side view, I'm gonna kind of put it about right here, and then we're gonna start peeling these back. You're gonna see the equilateral triangle, and there it is, equilateral triangle. So I can peel those all the way back, and no matter what, I'm looking at an equilateral triangle every time. So if I take the area of every last one of these as I keep going, all the way till I get to the end, boom, stop. Once you calculate all that up, then you'll know the volume of this shape. So this is a solid with cross sections of an equilateral triangle. That's what it looks like from the bottom. These are the sides of it. And now we're looking at the top of it. Known cross sections. There we go. All right, so that's pretty much all I wanted to go over today. I wanted to go over one example and show you the many shapes that we could find using cross sections, using the computer and everything. This software that I use today, this one's a little different from the one I used yesterday. This one's called WinPlot. Pretty straightforward. You just throw in your functions and press a button. It does the rest. So I like showing my 3D figures using WinPlot when we do cross sections. I like using this for it. It's pretty fast too.